But there's links to everything on the webpage. So what we did, we started out by working through classical field theory. So we developed a classical theory for a scalar field, and then the beginning of last week we started to quantize it like we would in normal, when we make the jump from classical to quantum mechanics. We promote observables to operators, and then we, solve Schrodinger's equation or something like that. But what we did was we followed the kind of the analogy of a simple harmonic oscillator. So we followed the path of how you quantize the harmonic oscillator using annihilation and creation operators, right, to basically factorize the Hamiltonian. And in the process, so we got to a point where we were able to write down a quantum theory, right? And then we talked about the LSZ reduction formula, which basically gives us a path to get from the theory part to making predictions for observables, okay? And so we derive something called the LSZ reduction formula, which is that beast there. So this is for a n to n prime type of interaction, but we started out by just doing 2 to 2 type scattering, right? And so basically what it boils down to is all you have to do is compute these things that we call correlation functions. So they're basically time-ordered products of the field operators, the vacuum expectation value of that, and then just do some derivatives and take some integrals, okay? And so it sounds pretty simple, but like I said, it's not, okay? And we'll spend, basically the whole semester and most of next semester too, learning how to compute these correlation functions, okay? And like I said, once you compute the correlation functions, life is simple because, we'll do those derivatives and integrals, we'll do them one time, okay? And then I'll show you a shortcut, which is, the way that Feynman did it, okay? So what we do, so last time we said, okay, you can keep going on with the canonical quantization way of doing things, but it starts to get messy, especially when you bring in interactions between the fields, and when you bring in multiple fields, it gets even more messy. And so what we wanted to do was to work out, to take a different path, pun intended, of quantization, and that is the path integral way. Okay, and so the path integral way is built on basically trying to compute transition probabilities or transition amplitudes. And so we started out by talking about transition amplitudes and scattering theory. So just basic, quantum mechanics, not really even talking about fields yet. And we talked about how you would compute this thing if you could discretize space, right? So we use this story of Feynman basically chopping up space into discrete pieces and then summing over all possible paths to compute the transition amplitude for a particle to start at some coordinate qi and end up at coordinate qf, right? And we know that all that time evolution is driven by basically the Hamiltonian. It's the generator of time evolution. So right, so we did this in quantum too, but I went back over it. How do you compute this guy? And we did it for a free particle, right? And we ended up finding that thing in equation 14, right? Which looks nasty, okay? Well, it doesn't look nasty there, but when you when you kind of unfold it and wrap everything, you see that this basically this integral over the path is this thing up in equation 13, which kind of looks like a mess because you're taking a limit, and in that coefficient there, you've got things blowing up, and it's not clear what's going on. But like I said, the nice thing about the path integral formalism is you can derive all these really complicated details, and then you just basically throw them out the window. Okay, you don't worry about them, and I'll show you why later on. And that is a kick-ass tan, man. I'm telling you right now. I don't know where he went, but oh yeah, that's right, that's right. Nice tan. So then I went on and I said, without proof. So that was an easy case of a free particle, right? And I said, what if we put in a Hamiltonian that has some general potential term that only depends on the spatial coordinates, And we end up getting something that looks like equation 16, which we ought, we immediately recognize that stuff inside the exponential as the action. In other words, the time integral of the Lagrangian, right? And that looks great. I mean, that's that's how you would compute the transition amplitude, right? But how the hell do you do that? I mean, you look at that and it's like, it's beautiful, it's awesome, but what are you going to do with that, right? Well, that's not for this class. That's another discussion in itself. But what I'm going to show you today is why the path integral formalism is so handy. It's so useful when it comes to computing things in quantum field theory. Okay. All right. So that's the path integral in equation 17. I think that's where we stopped, right? People that were here last time, maybe.
Yeah.
Okay. All right. So what I want to show you is now what happens if you take this transition amplitude and say you want to compute the quantity where you stick a position operator in the middle, in between these two states, right? And we know we could go back and forth between the Heisenberg picture, where the operator depends on time, or the Schrödinger picture where the operator doesn't depend on time, but the time evolution is given by sandwiching this guy between these two time evolution operators, right? From time, from time t prime to t double prime. Okay, so how do you compute these guys, right? Well, if you go back and you put that factor of q in on the left-hand side, right, and you go back and you do all those same steps that we did before, like when we computed just the transition amplitude, you find that the only difference is this factor of little q on the right-hand side. Okay, that's all that's going to happen, because what happens is that big Q hits one of the states, one of the Q states, and it just gives you the eigenvalue Q. Okay, and that's fine. All right, so that doesn't really help me. I don't know what the hell that means, or how I'm going to use that. But think of it in the opposite direction. In other words, suppose you're given this quantity. Right, somebody says compute this thing. And now you're like, oh my God, I'm in big trouble, all right? But let me show you how you can do it using a few tricks, all right? So let's say we want to compute that. Well, if we work in the opposite direction, right, this guy is just going to be, some expectation value or some matrix element of two Q operators, right? And like I said, we always want to keep time. We want to keep the order of time. What do I want to say? We want to keep it, in the correct order. So we always have these time ordering operators that we put in, basically by hand. They're just there to remind us to keep things in time ordered. Okay. Right. Okay. So this is where you can start to see why this is useful, right? So this thing, I have no idea. This starts to look like what we saw in the LSZ formula, right? If you think of these Q's in terms of the phi's, right? This is like these correlation functions, right? So if I can think of a way to compute this mess, then I have a way to compute what these correlation functions are, right? And that's the name of the game in quantum field theory, is computing those correlation functions. Because once you have those, then you're off and running. You can compute the S matrix, you can compute, scattering amplitudes and cross sections and all the other fun stuff that you do in quantum field theory. Okay? All right. Okay? So the tool that we're going to use, all right, so we're going to use a couple tricks, all right? But the main tool that we're going to use are functional derivatives, okay? And functional derivatives, when people first see them, if they've never seen them before, have you guys seen them in math methods or anything like that?
I don't.
Derivatives of functions with respect to functions.
Wait.
Okay.
Wait a minute. Maybe.
Okay, it's all right. It's all right. We'll go over it ad nauseum, so don't worry about it. Okay. So a functional derivative, like I said, it's a derivative of a function with respect to that function, but with a different parameter, with a different argument. Okay. And it works exactly like the usual derivative. right? So if I take a derivative of x1 or xi's, like, you know, if I took a derivative of y with respect to xj, let's say z, I would get a Kronecker delta function. It's going to be 0 unless xi and xj are the same, right? It works the same way in functional derivatives. The only difference is it's a delta function. It's a Dirac delta function in terms of T1 and T2 parameters. Okay? All right? So don't worry about, you know, where is this coming from? This is a tool. This is a trick we're going to use. Okay? All right? So we're going to use this functional derivative trick. All right? And the way we're going to use it is we're going to take the Hamiltonian and we're going to add new terms to it. Okay? We're going to add new terms that are going to have, our Hamiltonian in general is going to be a function of P and Q, right? The momentum and the position. We're going to add new terms to the Lagrange, to the Hamiltonian, that are linear in Q and P, and they have coefficients F and little h. Okay? This is just a trick. I'm not doing anything, you know, fundamental or anything like that. I'm just adding these two terms. Okay? So I'm going to add these two terms, and as long as I take, I can't take Q and P to 0, but I can take these functions to 0. They're just dials, you know, that I'm putting in by hand. As long as I turn those to 0, at the end of the day, it won't mess anything up, right? Okay, everybody buying that so far? Okay? All right, so what do I do? Okay, so let me take our expression for the propagator, or the transition amplitude, which remember was the e to the I action, right? E to the I action is e to the I time integral of the Lagrangian, but the Lagrangian I'm going to replace with the Hamiltonian, right? In terms of the Hamiltonian, if you get this extra p, q dot term. And then here are my two new terms, remember, because it goes like minus h, so these guys flip signs, okay? All right, and I'm going to drop the time parameter dependence, the explicit time dependence, okay? But just remember that's always there. Okay, so I haven't done anything, but I just added on these new terms, and I know that if I'm going to compute any observables in the end, I'm going to have to set f and h to 0, okay? And just to remind myself that I have to do that, I put in these subscripts f and h. Okay, so that reminds me that these are kind of auxiliary terms that I put in by hand, and at the end I better take them to 0 if I don't want to screw up my calculation. Okay? Okay, so now let's take that guy. Okay, so this is our new propagator, right? And let's take a functional derivative of this guy with respect to the f function. Okay? Forget about the h function for a second. So let me do that. So let me take a functional derivative of the propagator. Right? So on the right-hand side, we've got the functional derivative of that, you know, path integral, right? And the functional derivative, the first thing I can do is it can pass through this guy. It doesn't depend on q. Right? So it goes inside and hits this exponential, right? Well, I know if I take a normal derivative of an exponential, I always get the argument times the exponential back, right? So that's what I get. So if I'm taking a functional derivative, I get the stuff back that's inside of the exponential, and then times the exponential. What am I doing? Why do I have... Okay, now I'm confused. Oh, okay. So, see, this is where I need to stick. Okay, so this functional derivative in the second line, it's already acted on the exponential, so it's only acting on this stuff. Okay? All right? You see where my confusion was? Because I'm taking functional derivative of exponential stuff.
Oh, yeah,
right?
I see.
And so I take that, I get the exponential back. So I should have written it like this. Of stuff.
Right, yeah, because then
Okay.
after you move it.
Right, because I've taken the functional derivative of the exponential, and now that derivative is acting on just that stuff in front of the exponential. Okay? Everybody with me? I'll try, maybe if I think of it, I'll try to change that. Now, functional derivative acting on this guy. What's it going to give me? Does it do anything to this? No. Anything to that? No. Anything to that? No. It's only going to give me this, right? And it's going to give me this. It only acts on the F term, right? And if I go back to equation 24, it's going to give me a delta function, right? So it's going to give me the coefficient Q, right, times the delta function, okay? And now, what can I do? Now I can use that delta function to do the time integral that came out of taking the functional derivative of the exponential, right? See that when I hit this guy, it brought down this this other time integral, right? But then when I carried this guy through the argument of the exponential, I get this delta function in the third line. Keep remembering that people listen to this. And then I can use this to do that, right? So what I end up with in the last line is the path integral, something that goes like I little q, and then the original e to the I action term with my extra terms, right? Okay? And that is, we reasoned earlier, that thing is what? It's, go back to equation 21, it's like the time ordered product of one operator q, right? See on the right hand side I have path integral of q e to the I action, right? And that's what I have in equation 27. I've got a path integral times q e to the I action, right? And that thing is the time ordered product of one of our q operators, big Q. Make sense? Okay? All right. It takes working through some of these sometimes, you know, to get the hang of it. But they work just like regular derivatives. So don't get hung up on the fact that they're functional derivatives. They work exactly the same way. You just get Dirac delta functions instead of Kronecker deltas. Okay? So I can do the same thing. I can now take, so I've already taken the functional derivative with respect to f. I can take a functional derivative with respect to h. And what's that going to do? This is going to pull down a factor of p. Right? Because when it, so now I have, I'm starting from here basically, and I hit this with the functional derivative with respect to h, right? And it's just going to pull out this factor of p. Okay? So I haven't done any, you know, deep, you know, quantum field theoretical stuff. I'm just doing math tricks, right? Okay? Right, but now you can, so like I said, you know, I'm just doing math tricks, and you can ask yourselves, well, you know, how is this helping us? Well, I've kind of, you know, hinted at how it's going to help us, because what we can do is we can compute time-ordered products of operators by taking functional derivatives of our propagator with these new auxiliary terms, right? That's what I've shown, that if, so here, like this guy, right, the right-hand side of equation 28 is just the time-ordered product of big Q and big P. Right? If I go back a couple of slides where we made those comparisons, right? All right, so this is how we go about computing these time-ordered products using the path integral. Okay, so we start with the path integral, right? And then we, you know, what it is, whatever it is for our theory, our Lagrangian, and then we add in auxiliary terms. Okay, these auxiliary terms are the FQ and the HP terms. Okay, and then using those relationships between, you know, path integral and time-ordered products that we had a couple slides ago, I can compute the time-ordered product products by just taking functional derivatives with respect to the function coefficient of whatever operator I want. Right? So if I want, a time ordered product of 5 Q operators and 3 P operators, I would have 5 functional derivatives with respect to F and 3 functional derivatives with respect to H. Right? Everybody buy it? Okay. Right? And I put the time ordered product in by hand, and that reminds me that, depending on if T1 is greater than Tn or whatever, that's the order that I put in. Okay? Well, like I said, this is nothing, there's no deep fundamental quantum mechanics here, right? It's just a trick. It's just a mathematical trick that we're using to be able to compute these things, okay, from the path integral. It still doesn't, it's still, probably for you guys, it's still a mystery at this point why we're doing this, right? Because we still don't know what the path integral is. But I'm going to show you that it doesn't matter, okay? Okay? Just know that at this point, we can get to these time-ordered products of operators by writing down the path integral and add on some new terms, and then just start taking functional derivatives. Right, so this is just a statement that a lot of times, so this is slide 13, a lot of times we're not interested in, we don't have states of definite position, right? We're dealing with some superposition of these, position states, right? So we're really working with kind of admixtures of, eigenstates of the position operator. And so I call those admixtures big I and big F, okay? This is just saying that, in general, we don't work with those states. And what I can do is I can always insert complete sets of states and get back to, something that looks like what we had before, the QI and the QF. Okay, the only difference is now we have to enter it over complete sets of states, but that's just nothing new. It's just, regular quantum mechanics that we learn about in, quantum 1, really, okay? All right, the really weird thing, and I'll show you how this works later on, is that we're always going to be interested in a situation where both the initial and the final state are the ground state. Right? And that should be completely weird to you right now. You should, be thinking Dr. Jackson is on drugs, or, those 9 and 10-year-olds finally got to him and he's completely off his rocker, right? But no, I'm not. Okay, so the thing that we're after is the transition amplitude from the initial state, from the ground state to the ground state. Okay? Okay. All right, and we give that guy a special name. We call it Z, big Z, or big Z if you're from Europe or not from the US. But I call it big Z, okay? All right, so what do I want to do here? Let's see. I read these notes today, but I don't remember reading this page. Oh, okay. So this is all right. Okay, so let me go back a step. Okay, so let me go back to equation 30. Okay, and I'm going to try to show that we can get away with just working with the ground state. Okay, so equation 32 is just a way of rewriting equation 30. What is it? Okay. Equation 30. The only difference is I've replaced QI and QF with Q prime and Q double prime for reasons that I don't recall why I would change notation in midstream, but I did it, okay? All right. So let's take our expression for this transition amplitude, right, for general initial and final states, okay? And we've always argued that anytime we're worried about scattering experiments, that we can take the initial and the final time to minus infinity and plus infinity, right? Because, in reality, you know, the initial starting points are so far from the interaction region that you can take these limits without causing any problems. And it's a lot of times it simplifies our lives. Okay. And let's consider the case where both the initial and final state are the ground state. Okay. So our expression for the z guy, if I take equation 32 and apply those limits and then apply the case where initial and final state are both ground states, gives me something that looks like equation 33. Okay. So this is what we want to work with, right? This is the transition amplitude that we're going to, you know, add terms onto and take functional derivatives and stuff like that, but it's still a mess, right? When you look at that thing, it's still a mess, okay? So let's see if we can use any more mathematical tricks to you know, simplify this thing, okay? So the first thing I'm going to do is I'm going to let the eigenstates of the Hamiltonian be denoted by the ket n, okay? So this is still going back to, you know, kind of the analogy of the simple harmonic oscillator, okay? And the energy of these states, if I hit this guy with the Hamiltonian, it would give me E sub n, okay? And I'm going to assume that the ground state energy is 0, okay? And remember, we can do this because all we're worried about are relative energies, right? So I can always add on an extra term to the Hamiltonian such that the ground state is at 0. Okay, it's just shifting the energy scale, okay? All right, so I'm going to do that. And what do I say? Note that the ket on the right-hand side. Okay, so the ket on the right-hand side that I'm talking about is this guy, this Q prime. And let's see how we can rewrite it. Okay, so Q prime, remember, has an argument of T prime. It's a parameter, right? It's a time-dependent ket in the Schrodinger picture, right? And I can pull that time dependence out of the ket and put it in an operator, e to the IHT prime, acting on the time-independent ket. Okay? So now what? Now I can insert a complete set of eigenstates of the Hamiltonian. So I'm doing in the second line. Okay, everybody with me so far? Okay? And then I notice that, what? If these guys are eigenstates of the Hamiltonian, right? So when that operator hits this guy, it just gives me this number. And this guy I can rewrite because it's just the wave function, right? It's the wave function. And remember, Q prime is now a parameter, okay? And n just denotes the, you know, eigenstate of the Hamiltonian. Okay? Everybody good so far? Yes? Yeah? Okay. All right. So now I'm going to use another trick, okay? I'm going to go back to the Hamiltonian, right? And I'm going to shift it by an infinitesimal amount, okay? And I'm going to shift it by an infinitesimal imaginary amount. Just to make things even.
Yeah.
Yeah, I know, your head's probably going to, like that scene from, what's the thing with Scanners?
Yeah.
You know what I'm talking about? Where the guy's, not to show it, yes. Anyway. So I'm going to take the Hamiltonian, and I'm going to shift it by an infinitesimal imaginary amount, okay? So I'm replacing h with h times 1 minus I epsilon, and in the end, I always take epsilon to 0, because I don't want to affect the physics, okay?
Why do you do that?
Well, you're going to see. You're like one of my 10-year-olds. Just let me get there. No, I'm kidding. I'm kidding. It's a good question why you would do that. It's not intuitive at all, right? It's just, I'll show you. So what I'm trying to argue is that we can get away with, you know, just using the ground state, the vacuum state, as the initial and final state, you know, irregardless of what we're trying to compute, okay? And this is the way that you prove it, okay? So I haven't really done anything. I'm just just using a trick, okay? So if I do that, if I shift the Hamiltonian, all it's really going to do is when I apply that shift up there, it's just going to lead to an extra term, right? That's multiplying the energy, okay? All right. So now let me pull out the first term, which would be n equals 0, okay? So if I put n equals 0 and pull it out here, right, and then I start my sum now at n equals 1, and this is all the other stuff that we had right there. Okay, the sum's just starting at n equals 1 now. Right? But we said what? We said that the energy, the ground state energy, we can always dial it to be 0, right? Because we're only interested in relative energy scales. Okay? So that means I can make E sub 0 equal to 0. So that means what? That this term is just 1, right? The exponential is just 1, and so I get some coefficient multiplying the vacuum state. All right? Now, what about the other stuff? This guy. Well, remember when we plug this back in, if we go back to the previous slide, you see that in equation 33, this guy, which the ket, Q prime, is really Q prime T prime. And we're taking the limit where T prime goes to minus infinity. Right, we argued we could do that because of the scales involved, right? The physical scales. So that's what I'm doing here. It's kind of bad notation, kind of bad, derivation. So blame it on me. But, so that's where this limit comes from. I'm saying if we go back and look at, where this guy goes, there's going to be a limit, right? Where T prime goes to minus infinity. Okay. And remember, we're holding this epsilon constant. We can take it to 0, right? When we're ready. Okay. So if I take T prime to minus infinity, what happens? If I take T prime to minus infinity, right, and what's going to happen? So the first term is just going to, it's just going to give me a constant term, right? Because as I take T prime to minus infinity, it's just going to give me, it's going to oscillate very fast, right? But it's not going to blow up or die or anything like that. It's some constant term. But here I've got this minus I multiplying this positive I, that's 1. Right? And then I get e to the e sub n multiplying epsilon multiplying t prime. But t prime I'm setting to minus infinity. Right? So that term is going to dominate. That minus I epsilon t prime term is going to dominate when I take t prime to minus infinity, and it's going to kill it off. Right? It's going to go to 0. The whole term is going to go to 0. Okay? All right, so just using this little trick where I add on a small piece to the Hamiltonian, and then I take these limits of t prime going to minus infinity, and you can show the same thing for the bra. The bra on this previous page, Q double prime. So you do the same type of derivation, and you get the same result. In other words, if I add this small piece onto the Hamiltonian, which I'm always allowed to do as long as I take epsilon to 0 in the end, that means that the only thing that's going to survive is the ground state. Right? And if there's only one state, then this, this is basically the normalization factor, it's just 1. Right? So that means that if I go back to equation 33, and I take those limits, I add that, first I add that little piece to the Hamiltonian, and then I take those limits, all I'm left with is basically what I argued before, which is all we have to worry about, it's like equation 31. All we have to worry about are the initial and final states. All that other mess goes away. Okay? You understand? You know what I mean? So all this mess, when I say I'm working with, the F and I states, all this stuff goes away, and I'm just left with this. Okay? All right? Cool. Where was I? I did this. Okay. Yeah. So just to summarize, we get, as long as, when we make this replacement, what I like to, this is what, in the business we call the I epsilon trick. Okay? And you'll see these I epsilons come along for the ride, for the rest of quantum field theory. Okay? Just know that you're always setting epsilon to 0, and this is where they come from. Okay? So from, in months from now, when we're doing, QED, and you look at the propagator and you see these I epsilon, and you're like, oh shit, I don't remember where did those come from. Remember this time, remember this point in time space, right? Where I'm saying they come from this trick, right? Just putting in this I epsilon piece because we just want to work with the initial state, the final state being the ground state. Okay? All right, so that means in the end we can write the path integral, which was, the transition amplitude basically, as just the, overlap between the ground states with these new auxiliary terms added in. Okay, the new terms coming in because I want to be able to compute correlation functions, right? The time-ordered products of field operators, all right? Okay. All right, so that is all for non-interacting quantum theories, all right? So that's the boring stuff. Okay, so now we want to add in interactions because we want to consider theories where we have interactions and we can do scattering experiments and we can do all this cool stuff. Okay. All right. So that means I'm going to have to add in a new term to my Hamiltonian. Okay. And this new term to the Hamiltonian we're going to assume is small. Okay. So we're going to use perturbation theory, right? And when we studied perturbation theory back in quantum 2. Right, we always said that when we talk about perturbation theory, the Hamiltonian breaks into two pieces. A simple piece, simple meaning we know what the solutions are, and a small piece, meaning that we can do a perturbative expansion, right, when we try to compute observables, okay? All right, so that means, so I'm going to write the Hamiltonian like this, in terms of the simple piece and the small piece, okay? And so that means that my path integral is going to become this. Okay, so for the time being, I'm just dropping the I epsilon piece because it's not important at this point. We'll put it back in a minute. Okay, and so we note that this guy is a function of P and Q. Right, it's always a function of the momentum and the coordinates, and the perturbation piece is also a function of P and Q. Okay. But what I'm going to show you is that, because we're always going to assume that we know how to compute the unperturbed path integral, right? So we're going to assume that we always know how to compute the case when this guy's not here, okay? Right? But so I'm going to show you is using this path integral formalism along with this functional derivative plus auxiliary term thing. You can actually build this term by taking functional derivatives. Okay? So that's the path that we're going to take. Okay? So in other words, if H1 looks something like this, so H1 has some n number of Q terms and it's multiplied by m P terms, terms of momenta. You can actually build that term by taking functional derivatives of the path integral with H1 gone. Okay, I'll show you how this works. Okay. The nice thing about doing that, though, is that if that's the case, then you can actually pull this guy outside of this stuff. Because remember how functional derivatives work, right? They come in and they give you delta functions. Okay. All right, so for example, say I have some H1 term, all right, so here's my perturbation term. It's a function of Q and P. What I'm saying is that I can take that exponential piece, so it's exponential time integral of H1, right? And H1, whatever the form it is, of P's and Q's, I can build that form by taking functional derivatives with respect to F or H. All right? Everybody make sense? What I'm saying? Maybe not. It's okay. We can all hold hands, and, but no, I'm just kidding. I'll show you, how this works. Okay, but this is what you're assuming, right? That you're assuming that I know how to solve the path integral. I know what the answer is for the path integral in the non-interacting theory. Right? And the whole point of, or one of the points of putting these auxiliary terms in is that I can compute the perturbed path integral by building the interaction terms by taking these functional derivatives. Right? Okay, so if I had an H1 term, like I said, so if H1 was, something that looked like the harmonic oscillator. No, let's not use a harmonic oscillator. Let's use, so let's say H naught is the harmonic oscillator, right? I think we're gonna see this in explicit detail, but let me just sketch it out. So we would have something like m omega squared x squared. Okay, so this is the term, this is H naught. We know how to solve this, right? And then H1, let's say we added I don't know, let's add a quartic piece, right? So let's add in some term that looks like lambda x to the fourth. Or, well, let's do this, let's do p's and q's. P, or q, and q, okay? All right, so if I want to put this term in, where lambda is small, it's a perturbation, okay? So I can have my path integral be something that looks like this. Like I said, I go into this in more detail, but I don't want you to get completely lost at this point. So I can pull out the H1 term. So going from here to here, I haven't really changed anything. I'm just assuming that I can build these terms by taking functional derivatives, right? So here I would have exponential minus I time integral, right? And then I would have lambda, and then I want something that's going to give me q to the fourth, right? So I would take 4 of these guys operating on this path integral. Exponential, let me just write e to the I action. Okay, you see what I'm saying? Oh, to the fourth, sorry. Right, because I want to build something that's proportional to q to the fourth. All right, so when I take this guy and I bring it in here, and I let this guy operate, it's going to bring down 4 factors of q, right? Because it's going to hit this guy 4 times, right? And then when I put it all back together, I would get something that would look like if I started out with just h being, right? So I can construct this term by using these functional derivatives. And you say, why the hell would you want to do that when you can just write that freaking thing down? The answer is because I'm assuming that I know what this bottom line is. I'm assuming that I know what this number is, right? That I know how to compute the path integral in the non-interacting theory. So if I know what that answer is, then I just take functional derivatives when I have a perturbation, okay? All right, like I said, it'll hopefully become clear. I'm going to go through some examples, okay? But I just wanted to put it out there. Yeah, okay? And so what we do is we take, like we would take or I don't know what they call it. In quantum mechanics, I want to keep calling it like baby quantum mechanics or kiddie quantum, but you just had it last semester, so that would be, yeah, that would be kind of an insult to you. But but we just take a perturbative expansion, right? So if I want to consider this thing at first order, I would just have one term, right? But then if I want to consider it, the next leading order term, I would take an expansion of that exponential, right? So I take an expansion of the exponential. Okay. All right. Okay. So in general, it sounds complicated, and it is, but there's some things that simplify our lives a little bit. One is that we're only going to consider perturbative Hamiltonians that depend on the spatial coordinate or the field coordinate, okay? And that's just physics, right? We never run into perturbations. Well, we did run into one, I think, right? In the when we were doing the hydrogen atom, right? Because I said that we never had perturbations that depended on the momentum, and then like 2 weeks later we had a perturbation that depended on the momentum. Yeah, but so for now on, okay, forget about the hydrogen atom. From now on, we're only going to have these guys that depend on Q. Okay, so that means that this H1 is only going to be a function of the functional derivative with respect to F. Okay? All right. The other important thing is that we're only going to be interested in time-ordered products of Q's, not P's. Right? So that means that we don't even need this term. Right? Because we're never going to be computing time-ordered products of P operators. So why the hell would we even bother writing down an auxiliary term? That depends on P. All right? And for other reasons, the Hamiltonian is only going to be quadratic in P. Okay? So those are three very simplifying features because what?
That O down there, that's supposed to be a Q.
Yes. Yeah. Thank you. And P won't involve. Yeah, it should be Q. It won't involve O either.
Yeah.
But yeah, in particular, it won't involve Q. Thanks. Okay, so that means that our life has gotten a lot simpler, and actually it's simpler than what I've written down because we don't have to worry about functional derivatives with respect to H anymore, right? All we have are functional derivatives with respect to F. Okay, so this is how we're going to get the path integral for an interacting theory. Okay, we get it from the non-interacting theory and building up the interaction terms by taking functional derivatives. Okay, and like I said, this is the form that we're going to mainly work with. Okay, so we'll take like a 2-minute break, and I'll show you how this works for the simple harmonic oscillator. Okay. So how's Greece? Awesome. Yeah. Yeah. That's cool. Oh, what did you do? How you live?
I was in a study abroad, so get up early in the morning, go walk up a mountain to some ruins, have a lecture afterwards. So instead of sitting in some lecture hall,
Yeah.
taking photos, we'd be like pointing at the rocks,
Yeah.
which is nice. I go to a museum, have lectures in there.
Wow.
Walk down the mountain again.
So it was like it had nothing to do with physics. It was.
No.
Yeah.
Yeah.
Nice. That sounds really nice.
Yeah. There was a lot of beaches involved.
Yeah.
A lot of food. They gave us, I don't know if this is true elsewhere, but in Greece, almost every restaurant you ask for a shot, they just bring you shots.
Shots. Something
like
lost in
free
translation. Or they're trying to get you to tip more.
I don't know.
Yeah, working the tip.
They bring you like, there's one time we were in Heraklion on Crete, and the waiters will like call you into the restaurant and say, oh, I think it's time for you to eat some food, or oh, we have a great view of the Acropolis, or, depending on where you are. So one guy calls us and he's like, free holy water and dessert afterwards on the house.
Yeah.
Okay, sure.
Yeah.
So we go there, and he's like, where are you from? Oh, from Texas. He's like, lassos, cowboys, bang bang. Like, no.
Oh,
exactly.
yes, yeah.
Right.
Yeah, I've known a few people who've had that problem. Luckily, with the few times I've been on my voice, and always makes people not associate me with Texas.
Yeah.
So I don't have to deal with that as much.
Yeah.
But dude, my legs got ripped. Like, you walk up and down mountains all day.
Yeah.
For like hours every single day. It's awesome.
Yeah.
then come back here, everything's just flat. It's
Yeah.
so flat. I never
Yeah.
used to think DFW was so flat, but we don't even have hills here.
Yeah.
There's no hills.
Yeah. I remember I spent the summer in Colorado, like up in Boulder.
Yeah.
And it was like that. It was everything, because at the time I lived in Florida. It was in the summer. So I went out to Colorado, lived there for a month, and it was drought, it was a drought. But yeah, we're in lectures, but then the rest of the time we were hiking. And then when I came back to Florida, I couldn't believe like how green everything was first. And then when I walked out of the airport, it felt like I was walking around in soup because the humidity was like just so unbearable. It's just so crazy. But yeah, I know what you mean. Like, a lot of times, someplace, and then you come back home and you're like, this is not what I remember.
The views were great too. I mean, for lunch or dinner, I'd buy a sandwich and then like walk up some mountain.
Yeah.
And watch the sunset over the ocean or something.
Yeah. That's crazy.
Yeah, it was great. Full time I was there, I was like, I live in the wrong country.
Yeah.
We live somewhere with mountains and beaches.
Yeah. Yeah, unfortunately, Chicago doesn't have a ton of mountains.
Some beaches, there's the lake, so
Yeah.
that's one thing.
Yeah. Big mountains of snow.
Yeah, so I didn't think environment would be a big deal to me, but now wherever I eventually go to live,
Yeah.
I'm gonna need some good nature.
Yeah.
Need some mountains.
Yeah. It's,
What's funny is my wife Rachel lived in Florida her whole life. Basically, only left the state for a few days and never really got to explore whatever. And so Florida's very flat. And so when we were driving here, we went over some pretty massive hills. And she's like, "Why is my car like struggling?" She's like, she thought her car was broken because like she didn't know to like you have to accelerate more.
Yeah.
And then slow down when you're going down the hill. And so she's like, my car's not going to make it. It's not going to make it. I'm like, what are you talking about? She's like, and I'm like, call me the next time your car starts doing this. So we're in this one like really hilly area. And she's like, it's doing it all the time now.
Yeah, it's called gravity.
It's kind of like, you ever heard of people who say lived in a jungle all their lives, and then they go out onto the plains and like, why is everything so small over there?
Yeah.
And you walk up and it's big. I don't understand.
Yeah. All right. Get back to it. All right. So we've gotten to the point where we can compute things in terms of the path integral. All right. And we've learned a couple tricks along the way, right, of how to simplify our lives a little bit. And now what I want to do is try to show you how that works for the quantum mechanical simple harmonic oscillator. Okay, so the harmonic oscillator. Right? And so what I want to do is just show you all this in action. Okay. All right. So let's start with so the unperturbed Hamiltonian for the harmonic oscillator. All right. And I'm going to use big P's and big Q's just because that's what we've been using before. Okay. In our earlier general discussion. Okay, so the Hamiltonian looks like that, right? And we know that, if we want to simplify things a lot, we can use this I epsilon trick. So we can shift the Hamiltonian by minus I epsilon, right? And so that means both of these terms are going to be shifted by minus I epsilon, right? But I can simplify things a little bit by using the fact that this guy is small, right? So I can rewrite this as 1 plus I epsilon in the denominator, right? And so that means that it's just a kind of an observation that if I shift the Hamiltonian by minus I epsilon, it's like I'm shifting the mass, the mass parameter by plus I epsilon, and this m omega squared, which is basically the omega squared by minus I epsilon, right? Remember, omega, without that thing that we can't say in this class, H bar, okay, we have outlawed that term. Omega is just the energy. So it's telling me that when I shift the Hamiltonian, I can, make these replacements, okay? So that's a quick and dirty way of doing this shift, right? Is this the shift, the mass parameter, and then the m omega squared term, okay? So with these replacements, my Hamiltonian, but my path integral is going to look like this, okay? And so you look at equation 47, and you're like, holy crap, what am I going to do? Okay, so I've got my Lagrangian in there, and you notice that I've already put in the auxiliary term, right? Because I know that I'm interested in computing these time-ordered products of operators. Okay, that's we know that in the end that's going to be our goal. Okay, so anytime you're in doubt, what should you do in quantum mechanics?
Guess a Gaussian.
Huh?
Guess a Gaussian.
Yeah. That one. There's a couple of things that you should do. Okay? guessing a Gaussian won't really help you on this one. It's a good guess. But the other one is, when in doubt, take a Fourier transform. All right.
So that must be Jackson's zeroth law.
Yeah. The first law is guess.
Guess. And the
That's a
second one
Gaussian.
is guess.
Yeah. And then the second one, if the Gaussian doesn't work, go to a Fourier transform. Okay. So let's take a Fourier transform. So what is a Fourier transform bias in this case? Because we're doing a Fourier transform between, time, space, and energy space, right? But what it's going to buy me is that, I don't know what the explicit dependence is here of the time of Q, but if I take a Fourier transform, the time dependence comes out in this exponential, right? And now I'm left with the Q twiddle that's a function of E, right? Don't worry about that, but just know that once I do that, then I'm going to be able to take that time derivative in the Q dot. Okay? All right? So that's what the Fourier transform buys me. Okay, so let's just roll with it. Let's do that and see where it takes us. Okay? So I can always go back and forth between Q of t and Q of e by taking Fourier transforms. Okay? And so like I said, if I take the Fourier transform of Q of t, and dot, so the dot gives me the d by dt, and then the Fourier transform of Q of t gives me this, right? And now I can take this time derivative and hit this exponential, because that's the only thing that depends on time. Okay? So if I do that, it at least allows me to get rid of the derivatives. Okay? So it just brings down a factor of minus IE. E has to stay inside the integral because this is an integral over E. Okay? And so that means what? So it means that my kinetic term, which I'm going to get rid of this annoying factor M, because I'm a field theorist, I'm a high energy physicist, so I can always get rid of constants and factors and stuff. I'm just going to set it to 1. Right? So my kinetic term now looks like Q dot squared over 2. Okay, so now I'm basically squaring this guy, this expression. Right? And now, this is another case where you have to be careful, right? Because I'm integrating over this dummy variable E. So if I square something like this, I better be careful and call my other thing that I'm multiplying times this guy by a different dummy variable. And I'm going to call it E prime. Okay? And like I said, I'll say it time and time again, be as general as possible. And if you do things right, these Dirac delta functions are going to come riding in on their white horses and save you, right? Just like in general relativity, the metric, factors of the metric tensor or delta functions always come in to save you, okay? So just be as general as possible, right? So the Q dot squared over 2 term becomes something that looks like this in equation 51, okay? And what do we see? We see that I have put in, so M, I've kind of abused, it's not really that great notation, but remember that with M comes this factor 1 plus I epsilon. Okay, so that's where that guy's coming from. Okay, everybody clear on that equation 51? Or I got it? This is q dot squared after a Fourier transform. Okay, so I would do the same thing for the potential term, right? So I have 1/2 m omega squared q squared. I'm setting m to 1, right? And q squared, again, it's a Fourier transform squared, so I have to be careful and have two different dummy variables that I'm integrating over, okay? And with that m omega squared term comes the 1 minus I epsilon, okay? So that's where equation 52 comes from, okay? And then finally, I can't forget about, you know, if I look back at equation 47, I'm taking a Fourier transform of everything. I better take a Fourier transform of my auxiliary term, okay? And to do that, I need to symmetrize it first, okay? So I need to first, because everything else was symmetric, right? I had q dot squared, I had q squared. Now I have this linear factor of q times this linear factor of f. So I'm going to first, to be safe, symmetrize it. Right, so I'm going to take fq and just write it like this, okay? And then take the Fourier transform, okay? And so when I take the Fourier transform, I get something that looks like this, okay? So the reason I'm doing that is because I have these dummy variables that I'm integrating over. So you can see that the arguments in this first term of equation 53 are the flip-flop of the arguments in the second term, okay? I'm just trying to be as safe as possible, okay? All right, so I put it all back together, and the stuff in square brackets from equation 47, let's go back to equation 47. So the stuff in square brackets is basically what? The action, right? 47 square brackets, everybody agree that that's the action with the auxiliary term, okay? Where am I? Here, okay, so let me go back. So I plug in my equations 51, 52, and 53 into the square brackets there. Okay, and you can see what? So I can pull out a factor of 1/2. I can pull out these two integrals here. This t integral is coming from equation. It's equation 47, right? Yeah, it's coming from that time integral in equation 47. Okay, and then I have what? I have this is my kinetic. This is coming from the kinetic term, right? That we worked out. This is coming from the potential term, that guy right there, right? And you see them being multiplied by q twiddles. And then here's my auxiliary term after I take the Fourier transform. Okay? And the one common factor I have to all of those is this e to the minus I, e plus e prime times t. Right? And so now you see another benefit of taking the Fourier transform, right? Because what is this guy? So the only time dependence now is out in this exponential, right? And I have this time integral here, right? And so an integral of an exponential that looks like this is nothing but the Dirac delta function times some factor of 2 pi. Okay? All right, so I can do that time integral that appeared in the action. Okay? So if I go back and I look at the action, and I do that time integral, it gives me a delta function in e and e prime. So that's going to allow me to do one of these integrals, the e or the e prime integral. So it's going to set, say, e prime equal to minus e. Okay? So that's where equation 55 comes from, because I've used that delta function. Oh, it killed off one of those factors. Okay. So I've used that delta function to do that e prime integral, and I'm left with equation 55. Okay, so you see I replaced e prime with minus c. Okay. And the term in square brackets can be written. Oh, okay, so I have this term, the term from the kinetic and the potential terms. I can rewrite it. Okay, so let me group stuff, the non-epsilon stuff and the epsilon stuff, right? So the first term is just e minus omega squared, right? It's coming from the ones. And then the other term is the I epsilon piece, it's e squared plus omega squared, right? But e squared plus omega squared is just a constant, right? Just a constant. And what? Oh, and epsilon is our free parameter, right? That we're always going to set to 0 anyways at the end of the day. So what we can do is we can just absorb this stuff. This is just a constant, so I can absorb it into epsilon. Really, if I was going to, there was a mathematician taking this class, I would call it epsilon prime, right? But I don't want to have to do that. I'm just going to call it epsilon. Okay, so I'm just know that epsilon now is epsilon times e squared plus omega squared, but it's all a constant, and then the end I'm going to set to 0, so who gives a shit anyway, okay? All right? Okay, so that means that that stuff in square brackets, I can write it like this. It's just e squared minus omega squared plus I epsilon. Okay, everybody with me? Yeah. Okay, so then the action, I can plug that back in, and I get here to the equation above, equation 57. And then, for reasons that are fuzzy right now, I'm going to pull out a factor of e squared minus omega squared plus I epsilon. Okay? So that means that the first term coming from the kinetic and potential terms just gives me, it's this q twiddle, q twiddle. Okay? And then my auxiliary term picks up this piece here in the denominator because I've factored that out. Okay? Now what? Okay, now comes the tricky part. All right? So now what we want to do is we want to do a change of variables. Okay? And maybe it's clear to you guys why I chose this form of change of variables. It's never been clear to me, but it just works out. Okay? So let me do a change of variables. Okay? And I'm going to define some new variable, x, and it's going to be q plus f, with f being over all that stuff. Okay? Because why? Because when I take q, when I take the q twiddle term, and I plug in that change of variables, what happens? So I get a term that goes like x twiddle. I get the cross terms between x twiddle and f twiddle, and then I get the f twiddle term. Okay? But the second term, what can I do to it? I can, what am I doing? The second term, second term in equation 57, right? That's what I'm talking about. So the second term in equation 57, when I do the change of variables, so I'm replacing q twiddle here with x twiddle, and so that looks like f twiddle, right? So I get this term, and then I get a term that goes like 1 over this mess squared. Right? And when I put those two together, I see what? What do I see? I see some stuff canceling out, right? Because, why? Because this is symmetric. All right, so these things are both the same thing, right? And what I end up finding is that this term cancels that term. So the last terms in equation 59 and 60 cancel each other, right? And so what my change of variable buys me is it gets rid of those wacky cross terms, right? In equation 57 that mix, that have f twiddle, q twiddle. Because now what I do is I was able to cancel those out. In equation 61, I get something that looks like this, which is this nice little, term. The first term that goes like it's x twiddle, right? And then I get something that goes like f twiddle, okay? All right, so that's what we get by doing this change of variable. So it looks nice, right? What do we do with it? Okay. Oh, and then the one other thing is that when we go back and plug this back into the path integral, the what do you call it? The the differential of the q is just dx. Okay, big dx. Okay, so that's I go from the integral over the path of q to the integral over the path x. Okay. Right. Okay, so we have a path integral that it's an integral over x. Right? And then I look at that expression and I'm like, okay, that's cool. So the first term inside the square brackets depends on x, right? So I have to keep that there, right? But that second term, the f-twiddle term, doesn't depend on x at all, right? So I can pull that completely out of this path integral, right? And if I pull that completely out of this path integral, I get this thing out in front, multiplying or operating on this guy, right? But this guy is exactly what we would have gotten if we had no auxiliary term in the beginning. Right? So in other words, it's our it's the path integral for no external, or let's I hate calling it external forces because it always confuses people. But it's what we would have gotten if we wouldn't have put in any auxiliary terms at all. Okay. In other words, it's the path integral that we know how to compute. That's what I'm trying to say. It's the simple piece, right? It's the piece that we know how to compute. All right, that's what we're assuming. Okay. Right. So this is what we would have in the case of no auxiliary terms, right? You can make a link, and I think this comes from Stridnicki. He tries to make a link between what we were calling auxiliary terms, between that and what we call external forces, right? So his Hamiltonian, when he wrote his Hamiltonian down, right, and he had this term that was like F times Q. Does that mean that's not? Okay. He was thinking of these guys as being like force terms, right? Forces multiplying position terms, right? It gives you energy. Okay. That's right. That's right. Right. Force times distance is work, right? And work is energy. Okay. All right. Good. I remember that. Fingers crossed. If I can only remember what del squared is called. If I can remember that, which is Laplacian. Give it to me. I'm ready. All right. Okay, so if you make that connection, right, and so this would be the term. So the second line in equation 63 would be the term with no external forces, right? And what do we know about the transition amplitude to go from one state? So for example, because on the left-hand side, we have the transition amplitude to go from the ground state to the ground state. If there are no external forces, what is this thing? It's just one, right? Because there's nothing to make it, make the state make a transition. So it's always going to be one, right? So what we have is this guy we know is just one. So in other words, when I take the general expression, what we started with, or in any case really, and we set the auxiliary term to 0, that's just one, right? It's just the probability to stay in one place if there's no external forces. It's just one, right? Okay. So that's awesome. That's a nice result because it means what? It means that my transition amplitude with the auxiliary term boils down to this equation 66. Okay? It's just the auxiliary terms, right? With this denominator, e squared minus omega squared plus I epsilon. Okay? So now what we would do is if we want to compute, time-ordered products of operators, this is what we operate on. This is what we take functional derivatives on. Okay? So that's pretty cool. All right? Well, the first thing we better do is we better go back now to our time space, right? We have an expression in energy space. Let's go back to time space, okay? And so that means I need to plug back in for f-twiddles in terms of these guys, okay? In terms of my f of t, all right? So again, I have to be careful. So when I plug in F twiddle E and F twiddle minus E, I better use different time variables. So I call them T and T prime, right? And I can do that, so I get this expression. And then if I group some stuff together, I get something that looks like this, where I've defined this guy, this G of T prime minus T, to be this energy integral of this mess. Okay? And anytime in quantum mechanics or in electrodynamics, when you see a capital G function, you should start sweating, right? Because it's a Green's function.
Yes.
Okay? And I personally hate Green's functions. Okay? Nothing personal to Green, but I just hate Green's functions. Okay? But luckily, we don't have to deal with them in here that much. But what I want to do is show you how to compute these guys, just if it ever, if the thought ever occurs to you, I wonder how you compute this Green's function. I'm going to show you, okay? So in other words, this is the Green's function for the simple harmonic oscillator, all right? And we all know what the definition of a Green's function is. It just, when the operator, what is it? When the operator hits the Green's function, it gives you a delta function, right? This is the definition of a Green's function. Something like that, okay? You can tell I don't work with the Green's functions a lot. All right? Okay. So like I said, we're hardly ever going to, we'll probably never need the explicit form of a Green's function. Thank God. More like thank Feynman. Okay? But what I want to do is just show you how to compute these guys, because it involves contour integration and what's the other thing that's linked with contour integration? The residue theorem. Okay. So let's have some fun with contour integrations and the residue theorem. Okay. All right. So the first thing you do is, okay, so I look back at equation 68, which is the definition of my Green's function. Okay. And I can notice that I can factor this guy. Right? I want to factor this into a term that goes like E plus or minus omega. Right? And I can do that because epsilon is a small parameter, right? So I can factor that and not really lose any generalities or I can do it without loss of generality, right? So in other words, I can factor this guy into something that looks like this. These two terms multiplying each other plus some order epsilon squared terms that don't matter because in the end I'm taking epsilon to 0. Okay? So I look at that and I remember now I think, okay, wait a minute, this is in the denominator and I'm doing an integration, right, over E, and all of a sudden I can see that I'm going to run into some problems, right, because when E hits this value, the imaginary value of, say, omega plus I epsilon or minus omega minus I epsilon, I get poles, right? I get divergences, right? Okay? One simplifying thing is we're in physics, right? So it's not some complex analysis class, we're in physics. So we're just worried about positive energies. So let's just worry about this pole. We can forget about this pole, okay? So let's just worry about this guy. All right? So what we can do is, use this method of contour integration, which I have to admit is another thing that I would put in the category of Green's functions that make me sweat, and I don't feel comfortable when I do them, but let me try to do my best over the next few slides and show you how to do it, okay? So this is my picture, okay? So I'm doing, can you guys see the picture? Okay, so I'm doing an integration, right, along E, right? The transverse plane is my imaginary plane, so this is the real plane. Transverse is the imaginary plane. So there's my pole, that cross-hatched thing, right? And the way that I do it is I do what's called, I push up the contour, right? So I make the integration not from minus infinity to plus infinity, but I wrap it around, right? And I wrap it around so that it encloses the pole, okay? And if I do that, right, I'm not changing anything, but it allows me to use this residue theorem, okay? And the residue theorem is just this. It says that if I have some contour integration, and it looks like this, I have some function of a variable z that I'm integrating over, and this guy has a pole at z naught, right? It's just equal to 2 pi I times the function evaluated at the pole. I'm not going to try to prove that to you because I don't remember the proof, okay? And if I'm saying stuff incorrectly or whatever, don't call me.
I think we proved it.
Okay,
Yeah.
good. All right,
Now,
thanks. Thank you, Dr. Musalak.
I definitely remember the half circles.
Yeah, okay. All right, so this is one of those few times that you actually use it, okay? And like I said, we're not going to need it, but I just want to show you how to do it, just in case, okay? So this is what, so we've pushed up our integration, we use the residue theorem, right? And if we go back and look at our integral that we have, for us, this z minus z naught is going to be equivalent to this guy, right? We're only looking at the positive pole, right? We're never going to have a case where we're going to hit that negative pole. And the function f of z is everything else, right? So it was that exponential and the piece, you know, the other part of the denominator. And so what it tells me is I use the residue theorem and I can just plug it in, right? And then I evaluate it at the pole. And the pole for us is omega plus I epsilon. And if I plug that in, I find that the Green's function, which is what we were calculating, just looks like this. It's some oscillating exponential. Okay? But it's not that simple because so that was for the case of t prime being greater than t, but I also have to account for the fact where t is greater than t prime, right? And so what you have to do is you have to go back and you put in, if I remember correctly, you put in some step functions, and then you do the two pieces separately, and then you can combine everything into an exponential that looks like that, okay, where the arguments are being taken the absolute value of t, the difference between t prime and t, okay? All right, if you guys are, if you're really interested, I can give you a homework problem where you can compute this thing, okay? I can see the interest just emanating from you guys, okay? So if you want, I can give you the homework problem, but just know that you have to be careful, and you have to account for both possibilities, where either t or t prime is the earlier or later time, okay? All right, so that's how you would compute a Green's function. Like I said, we'll never need it, okay? Luckily, and at night, say your thanks to Feynman before you go to bed, okay? Because we don't have to worry about that stuff. Okay, so finally, the last thing I want to do is I want to turn my attention to computing time-ordered products of operators. All right, so, and like I said, we're only ever going to consider time-ordered products of Q operators, or for us, when we get to fields, they're going to be phi, right, our field operators. Okay? And to do that, what we're going to do is we're going to use that kind of algorithm that we built up at the beginning of this class, which is we take our path integral, or I call it the propagator, right, where we've added in the auxiliary term, and we've already seen that it's just that simple integral with f and f over this stuff, right? And however many factors of q I want, I'm just going to take functional derivatives, okay? And then at the end of the day, when I'm done, when I'm satisfied that I've got as many q's as I want, I just set f to 0. Okay? Easy, right? So let's say we want to compute the time-ordered product of two operators. Okay? So if I do that, two time-ordered operators. So I've got QT1, QT2, and I put this time ordering operator in there by hand just to remind myself. Okay? And what we're saying is that so that means I'm going to take my path integral, right? I'm going to take two functional derivatives, right? One with f of t2 and one of f of t1, okay? But this guy we've shown is just this simple thing here, right? So it's exponential f, one has argument of t, one has t prime, and sandwiched in between is the Green's function, All right, I don't have to worry about what that green's, we calculated it, but who gives a crap, all right? Let's just call it G for now, okay? So now I want to take these functional derivatives, all right? So the functional derivatives are only going to hit those F terms, right? They're going to pass right through the G terms, okay? So the first thing I get is, so I get the two factors of 1 over I get combined, right? So that gives me 1 over I squared. And now let me take the first functional derivative. So I take the first functional derivative, I get the exponential back out, and then I need to take the functional derivative of the stuff inside the exponential, okay? So it hits the first term, it gives me a delta function, and then I get G times F of T prime, and then I have to use the second, then I use the multiplication rule, right? And so I would have F, G, and then a delta function in T prime, right? So everybody see what's going on? I'm taking functional derivative of this guy here, right? But it's inside of an exponential. Okay, so when I take the first one, right, it's going to give me the exponential back, but then I have the functional derivative of the stuff inside of here. Okay, so this is going to give me first the delta function in T and T2, right, times G times F. And then the second term would be F, G, delta function, T2 and T prime. Okay? Okay, so that's what the first line is. And I always put that F equals 0 thing at the end to remind myself that at the end I better set it to 0. Okay? Okay. All right, so that's that, and I can simplify that because I can use the delta functions to do one of those time intervals, right? In the first line there, I can use the delta function to do the time interval. All right, and then at that point, I can set no, it's all right. Okay, so I use those delta functions. Now I still got one more delta function, or one more functional derivative to take, okay? And so again, what's going to happen is it's going to hit this exponential. It's going to bring down, or I'm going to get the exponential back. It's going to bring down a factor of the stuff inside, and then I have to take the derivative of the stuff inside, right? And then I have to take the derivative of the stuff that was left over from the first functional derivative, right? But there's a simplifying thing that you notice, right? And the simplifying thing that you notice is that if I have a term left over and it's got a factor of F in it, right, after I take the function derivative, I can get rid of that, right? Why? Because at the end, I'm going to take F equal to 0, right? So if I have terms that, after I take the functional derivatives, and I've got F left over, I know at the end, I'm always taking F to 0, right? So I can just, along the way, and you'll see what I'm talking about. If you work through a couple of these examples, you'll see that, as you go down, you're going to have terms that there's going to be an F left over. You can tell there's going to be an F left over, right? Because there's just not enough functional derivatives to get rid of it. So you can always just drop those terms, okay? And so in the end, out of all this mess, I find that the time-ordered product of two operators is just basically a Green's function, okay? All right. And like I said, you can keep on doing this, until you're blue in the face, right? Until the cows come home, like we would say in the South, okay? All right. One of the things you notice is that, so we did 2, right? You can go off, you can do 4, you can do 3, you can do 15. It doesn't matter. But what you find out is that any time-ordered product of operators where you have an odd number of operators is going to be 0. And it's going to be 0 because you're never going to, all your factors are going to have leftover F's in them, okay? And you can just prove this to yourself by whatever it's called, deduction or whatever. What's the fancy term? Is that what it's called, deduction? And you do things and you just keep doing it. Induction, okay. I knew it was something deduction. All right? But you can prove to yourself that anytime I have an odd number of operators, it's 0. All right, so if I give you on the qualifier, if I say compute time ordered product of 45 45 Qs, no, but you guys are going to be lucky because you took this class.
Yeah.
Those people that didn't take this class, screw them. Okay, so don't tell them. All right. So when I say consider the, when you see a problem, consider the path integral for a simple harmonic oscillator. Compute the time ordered product of 45 position operator. Right? You're gonna be like 0, and they're gonna sit there and they're gonna try to come up with some bullshit, and then they're gonna get a 0 because they didn't take this class. All right. All right. Anyway, so anytime you have an odd number of operators, it's a 0. Okay, so that tells us that the only non-zero, that the only thing that's left is even numbers of operators, right? And so, for example, if you go through and you calculate the time-ordered product of 4 operators, you get 3 terms, right? And it's just, you find out that it goes by the sum over the pairings. Right? So you see the first term pairs T1 and T2, T3, T4. Second term pairs T1 and T3, and this T2 and T4. Right? And this guy is T1 and T4 and T2, T3. Right? But if you ask for 6 or for 8 or for 10, right off the bat, you don't have to go and compute them. You can use this theorem. I can't remember what the name of this theorem is called. Did I put it in the slide? No, I didn't. It's some theorem. I can't remember what it's called, but I'll remind myself before Thursday. Okay? I almost had it. It just almost came to me. But anyways, it's a theorem that says that, anytime you have an even number of operators, it's just the pairings. You just sum over all the possible pairings. Okay? Okay, so I'm going to stop there. But what I want to show you is, so this is the kind of thing that Feynman noticed. He was learning this stuff, like they, did it back in the old days, and he started noticing that these things take they have patterns. Like so what I'm doing is I'm computing basically this guy is the probability, the transition probability that I start with 2 particles, say at Q1 and Q2, and they end up at Q3 and Q4, right? So what he's noticing is that, so let me just put these at T1, T2, T3, and T4, right? So what he starts noticing is that these things make patterns, right? So the first term goes from T1 to T2, the other one goes from T3 to T4, right? So it's from T1 to T2, and from T3 to T4, right? And then the second term would be a similar diagram, okay, that goes not from T1 to T2, but it goes from T1 to T3, right? And then this one goes from T2 to T4. And then finally, the last diagram is where they're crisscrossed, okay? And so he starts to see this pattern that, even in this simple theory where you have this, so that we don't have any interactions yet, okay? So that's why the particles, if you will, are just flowing from one space-time point to another space-time point. They're not interacting. They're not bouncing off of each other, right? But even for this case, he starts to say, oh, okay, I see something happening here. I see these, what the time-ordered product looks like in terms of Green's functions, but who the hell wants to work with Green's functions, right? I want to go off and play my bongos. I don't want to worry about Green's function. So let me just write down some diagrams and then write down some rules for what does this diagram mean? Well, this diagram is 2 Green's functions glued together, right? And I know that I have to sum over these diagrams, okay? So this is we're starting to get into that, and we'll get into it deeper over the next couple of lectures, okay? When we start to add in interactions, okay? But like I said, so that's the simple harmonic oscillator. The good news is, well, the bad news is we haven't done any field theory yet with this stuff. Okay, so this was all quantum mechanics, baby quantum, kitty, what do we say, kitty quantum? Okay, kitty quantum mechanics. Okay, the good news is we've done all the heavy lifting. Okay, so when we go and apply this to a field theory, which will apply to the Klein-Gordon field, we've already seen that there's a strong kind of correlation between the harmonic oscillator and the way we can do field theory. We'll actually just, and I think what I did was I just kind of copied and pasted this talk into the field theory version of this and just made some changes, okay? So you'll see we'll do all those same steps. We'll start with the Hamiltonian, we'll shift the Hamiltonian, we'll do all the same change of variables and all that same kind of garbage, okay? All right, so that's what we'll do next time, but I'll kind of breeze through it because we've already done all the heavy lifting, all right? Okay. All right, homework was due today. Did you guys know? Okay, I'll give you one extra day. Oh, you didn't get the email? I'm just kidding. There's no homework. There might be one day. Don't cross me, okay? All right. All right, I'll see you guys on Thursday.
I reviewed over the bad graph thing. I also found the notes I took from when that we had to use it in particle physics. So I think
okay.
I'm ready for the, trying to give lots of stuff for the
Okay.
things.
Okay, good. Yeah, just let me know if you run into problems.